So this is the lecture number 2 of convection. Today we will be discussing the classification of fluid flows. Okay, in convection, fluid flows play an important role in deciding the rate of heat convected during a process. Okay, so let us start our discussion. So our objective is to visualize the development of velocity and thermal boundary layer during flow over surfaces, gain a working knowledge of dimensionless Reynolds, Prandtl and Nusselt number. So we have earlier studied the Nusselt number, but we again want to have some basic knowledge of these dimensionless number. So these are the let us start with the classification of fluid flows. Okay, so viscous first type of classification of the fluid flow is given as the viscous as versus inviscid or inviscid type of flow or inviscid region of flow. Okay, so viscous flows are those flows in which the frictional effect are significant. So in other words, we can say that the effect of viscosity cannot be neglected during the fluid flow, while in case of inviscid flow regions or the inviscid flows, the effect of viscosity can be neglected. Like in many practical problem, there are regions typically regions not close to the solid surface where viscous forces are negligibly small compared to the inertial or pressure forces. Okay, so that is why in a fluid flow, or let us say through a pipe or through a channel, maybe there are some portion through which the flow is viscous, and there may be other region where the flow is, even though viscous, the viscous effect is so negligible that we can neglect the viscous forces. Okay, as you can see in this figure, this is a plate. So the fluid flow near this region is, you can see, this is the viscous flow, while the flow in this region is inviscid flow. So the flow of this is an example of a flow of originally uniform fluid stream over a flat plate in the region of viscous flow next to the plate on both sides, and inviscid flow away from the fluid plate. Okay, so this is the another example of internal versus external flow. So external flow, as you can see, the flow of an unbounded fluid over a surface such as plate, wire and a pipe. Okay, so means that the fluid is flowing over a surface, okay, not inside the surface, while the internal flow, you can see the flow of the flow like in the pipe, like in the duct, and it is completely bounded by the solid surfaces. Okay, so such kind of fluid flow are called the internal flow, and also they are their flow is a little bit restricted by the presence of the solid boundary. Okay, so water flows in a pipe is internal flow, and air flow over a ball is an external flow. So this is one example of flow of internal and external flow. Then again, the flow of liquids in a duct is called open channel flow if the duct is only partially filled with liquid and there is a free surface. So external flow, as you can see, external flow of it over a tennis ball on turbulent wake region behind. So this is one example of development of fluid flow over a tennis ball. Then another classification is compressible versus incompressible flow. Okay, so incompressible flows, in the incompressible flow, if the density of the flowing fluid remains nearly constant throughout, you can say throughout the flow, like in the case of the flow of the liquids, this kind of flow is called the incompressible flow. Okay, so the condition for incompressible flow is that there should not be any change in the density, or any change, if any change is there in the density, the density change in the density should be neglected. Then case of compressible flow, the density of the fluid cannot be neglected. Okay, because there is an appreciable change in the density. Okay, so the variation cannot be neglected, the change in the density cannot be neglected. So we can say that the density of the fluid changes during the flow. So like for example, high speed gas flows. Okay, so again when while analyzing rockets, spacecraft and other system that involves high speed gas flows, the flow speed is often expressed in terms of Mach number. So Mach number is basically associated with the compressible flows only. Okay, and Mach number is defined as the speed of flow to the speed of sound. If the Mach number is equal to 1, then the flow is called the sonic flow. If the Mach number is less than 1, then it is called the subsonic flow. If the Mach number is greater than 1, then it is called the supersonic flow. And if Mach number is very let's say 5 6 or more than 6, then the flow is called the hypersonic flow. Okay, so c is the speed of sound, and the value of speed of sound is 346 meter per second at room temperature and at sea level. Okay, so as you can see, the speed of sound is also variable. It depends upon the temperature as well as the pressure. Okay, so at the sea level and room temperature, let us say 25 degrees Celsius. So 25 degrees Celsius, and at the sea level, the average speed of the sound is 346 meter per second. Okay, so the gas often flows from often can be approximated as incompressible if the density changes are under 5%, and which is usually the case when Mach number is less than 0.3. Therefore, the compressibility effect of the air can be neglected at the speed under 100 meter per second. So these are the some of while calculating deciding between compressible and incompressible fluid, so we can take these things into account. Then and there is another kind of you can see classification which is known as the uh, laminar versus turbulent flows. So laminar flow, as you can see, it is a highly ordered fluid motion characterized by smooth layers of fluid flow of high viscosity fluids such as oils at low velocities is typically laminar, while the turbulent flow are highly disordered fluid motion that typically occurs at high velocities, and it is characterized by velocity fluctuations. The flow of low viscosity fluids such as the air at high velocities is typically turbulent. And then there is another intermediate type of flow that is called the transitional flow, where the flow actually alternates between laminar and turbulent. So it becomes difficult to identify whether the flow is laminar or turbulent type of flow. Then there is one more type of flow that is called the natural and forced flow. Okay, as you can see in this figure, this is a case of natural flow. Okay, so force flow is forced over a surface or a pipe by the external means such as a pump or fan. Fluid motion is due to natural means such as buoyancy effect, which manifest itself as the rise of warmer and thus lighter fluid and the fall of the cooler and denser fluid. Then steady versus unsteady flow. The term steady implies that there is no change at a point with time. So opposite of the steady is unsteady. So the term uniform implies no change with location over a specified region. The term periodic refers to the kind of unsteady flow in which the flow oscillates about a steady mean. Mm, device such as turbine, compressor, boiler, condenser, heat exchanger operate for long period of time under the same condition, and they are classified as steady flow devices. So two, one, two, and three-dimensional flow. This is another kind of classification. You have already studied these type of flows in fluid mechanics, and as you can see, the field is best characterized by its velocity distribution. The flow is said to be 1, 2 or 3 dimensional if the flow velocity in 1, 2 or 3 dimension respectively. Therefore the variation of flow a certain direction can be small relative to the variation of other direction and can be ignored. As you can see, this is the flow velocity. This is how the velocity develops over the period of time in the development of profile, velocity profile in circular pipe, v equal to brz, and thus the flow is in two dimensional in the entrance region and becomes one dimensional downstream when the velocity profile fully develops and remains unchanged in the flow direction. So there is one more concept that is called the velocity boundary layer, that again you have studied in, you are aware while you study with your studies of fluid mechanics, that the region of the flow above the plate bounded by delta, in which the effect of viscous delta is the thickness. Okay, so the effect of viscous shearing forces caused by the fluid viscosity are felt. Boundary layer thickness delta is typically defined as the distance y from the surface at which u equal to 0.99 v. The hypothetical line of u equal to 0.99 v divides the flow over a flat place into two regions. So the boundary layer, one is called the boundary layer, another one called is the irrotational flow region. So the viscous effect and the velocity changes are significant, while in the irrotational flow region the frictional effects are negligible, and the velocity remains essentially constant. So this is the velocity boundary layer. As you can see, this figure fully explains itself, that how the velocity boundary layer changes. So this is the typical boundary layer changes in the velocity of the velocity, and this is the you can see the development of boundary layer on a surface due to the no slip condition and friction. So as you can see, since because of the presence of boundary layer, the concept of shear stress also arises, and from the Newton's law of viscosity, we know that mu equal to del u over del y at y equal to 0. Dynamic viscosity equal to kg is this is mu is the dynamic viscosity, and this is the unit of dynamic viscosity. The fluid that obey the linear relationship above are called the Newtonian fluid. The most common fluids such as water, air, gasoline, oil or Newtonian fluids, and blood, liquid plus plastics are examples of non-Newtonian fluids. In this context, we consider only the Newtonian fluids. Wall shear stress, another concept is wall shear stress, and if we if we divide the dynamic viscosity with density, so it becomes kinematic viscosity. Okay, so wall shear resistance is given by the this formula, or Cf equal to rho v square by 2, and it is the friction coefficient, and or skin friction coefficient, and the viscosity of the fluid is a measure of resistance of deformation, and it is a strong function of temperature, and the friction force over the entire surface is given by ff equal to cf, f equal to rho v square by 2, and the friction coefficient is an important parameter in heat transfer studies since it is directly related to the heat transfer coefficient and power requirement of the pump or fan. This is the case of dynamic viscosity. Dynamic viscosity is at some fluid at 1 atmospheric pressure and 20 degrees Celsius. As we can see, these are the values, and these values are widely utilized while doing the calculation. So the summary of the present lecture is that this is we have learned many things. So one important we have learned today about the types of fluid flows, and also about the concept of shear stress and shear stress at the wall surface, and it is expressed by using this relationship. Okay. So these are some of the review question. The first question is, in which mode of heat transfer is the convection heat transfer coefficient usually higher, a natural convection or of force, convection, and why. Now another example, another question that you go through and try to answer this is the let us consider a hot baked potato, and will the potato cool faster or slower when we blow the warm air coming from our lungs on it instead of letting it cool naturally in the cooling air in the room. You try to explain what will happen, whether it will become warm or it will slowly cool. Okay, you have probably noticed this, and you will easily answer these questions. So these are the references from these two books I have referred for making this presentation. Thank you for your patience.